So it's my pleasure to introduce the first speaker of this morning. It's John Barrett from Nottingham, who's going to talk to you about it.
I forgot what I said. Knots and links in braided. Yeah. Okay, thanks very much. So it's a pleasure to be at this series. Particular focus on category theory in physics. Is that right? There's not a link to it. Is it logic? Logic. Okay. So I don't know anything about logic. Sorry about that. So it's really about category theory in physics. So I'm really a physicist, although there is a great temptation to write papers in mathematics. But I try and resist that as much as I can and stick to the physical questions. And the big physical question I'm interested in is the main question of fundamental physics, is the quantum gravity question, and how to unify general relativity and quantum theory. And in this regard, we can think of category theory possibly as a tool, as a mathematical language, possibly an actual tool for constructing the theory. And so the question is really, what are the physical applications of category theory? And I think it's fair to say that although categories come into physics all over the place, in various ways, there isn't yet any killer application for category theory in physics. So, I mean, you can think of the parallel story for Lie groups, that Lie groups for many years were thought of as some abstract nonsense that weren't really necessary, although they were used in specific examples. You could actually do all the calculations without really knowing any theory. And it wasn't until Yang-Mills theory and the classification of particles by representations of various Lie groups that theory actually became a sort of essential part of physics. And we haven't yet got to the stage of recognising the Yang-Mills category theory. You see what I mean? So the question is, where should we look for it? What sort of clues are there? So certainly a lot of category theory is very quantum mechanics-like in its features, and so we might expect it to come in various ways. And one way that it does come in is in three-dimensional quantum gravity. So by three-dimensional I mean three space-time dimensions. So that's one less than usual. So this isn't real physics, this is make-believe physics. But nevertheless it's interesting models. And you can see some use of categories in there, specifically monoidal categories. And it's sort of slightly non-trivial, although you can sort of do the whole theory and not really know any category theory. So it's not really totally essential yet. So if you move up to 4 dimensions, some people have proposed a 4-dimensional model based on the experience of doing 3-dimensional quantum gravity, which works, by the way. There is a sort of mathematical theory and so on. In 4D models, there are some models proposed, but they're not really right yet. I mean, I don't think we really know what a good 4D model is. But one of the features, if there was a right theory, is it should be much more sophisticated than the category theory, because going up from 3 dimensions to 4 dimensions is adding 1 dimension to the higher category language, and that's extremely non-trivial exercise. So you go from, for example, monoidal categories to monoidal 2 categories, which then take a lot of paper and diagrams to describe and have lots of non-trivial features and so on. Okay, so that's one possible place, but as yet I think we don't know the right examples for the 4D applications. So hints from other places in physics. Well, noncommutativity is starting to come in various theoretical enterprises in physics, and noncommutativity has possibly something to do with categories. And there's a whole large subject called noncommutative field theory, where people take the usual quantum field theory, which is something to do with the algebra of functions on space-time, and then dream of non-commutative deformations of these algebra functions and construct the quantum field theory in the same way as usual, but just paying regard to this non-commutativity. And this is a large subject, and there's lots of literature on this. Non-commutative field theory. And for example, there's some body of results that say that the renormalization properties in this non-commutative world are actually better than they are in the standard commutative setting. And so there are scalar field theories, for example, 5 to the 4th is better behaved in the non-commutative setting. And there's some interesting body results and insights, and people are starting to extend this to gauge theories, fermions, and so on. But as yet, there's no new physics from this enterprise, although it's sort of interesting, and perhaps it's sort of like Chris's project, but in a different direction. Instead of any space-time, it's any non-commutative deformation. It's seeing quantum field theory and renormalization theory in a more general framework and seeing what survives, and possibly what's enhanced in this more general framework. But as yet, there's no actual sort of real physical results. We can't, there aren't predictions and so on. Vastly new theories. Non-commutativity seems to come in the standard model of particle physics, and there's a non-commutative structure for the classical Lagrangian there, and this is predictive. It gives some predictions of the parameters in the standard model, but as yet there's no quantum theory involved in that. The quantum field theory is the same as the usual one. So there's a little hint, but it's a very, very small, tiny hint, if you like. And then that brings me back. So that's non-commutativity, big subject, but only a small number of hints. Brings me back to the 3D gravity. Well, the 3D gravity suggests a braided quantum field theory, which I'll explain about. And as yet, the literature on this is very, very small. This is a small subject. But I expect it will get larger, and so there's plenty of things that haven't been done and so on in this subject. So it's an interesting subject from that point of view. And there is some relation between these things, being non-commutative and braiding and so on, sort of go together a lot, but the technical setup is somewhat different. So this is what I'm going to talk about. I'm going to talk about the braided quantum field theory. It's a little bit about the relation to 3D gravity. Okay, so this is what we do in perturbative quantum field theory. Okay, so I'm not going to talk about this. I'm going to talk about that. So this is the usual approach to quantum field theory in the non-braided or non-commutative setting. We calculate expectation values of various polynomials. So I'll write down the expression, some sort of integral. Explain what everything is. So the variables here lie in some vector space. Here there's a vector. I'm integrating over that vector space with some Gaussian measure here, and a matrix. So this is Gaussian here, so non-degenerate matrix. And P and Q are polynomials. And we want to find the expectation value of Q in the system. And I is a normalization constant, which is basically the same thing without Q there, so that the expectation value of Y as well. So we think of P as the interaction.
What vector space is this?
And Q as the, we're called the external legs. Well, any vector space you like, but normally it would be in physics it would be a space of fields, functions on the space-time manifold. But we can have any vector space. It could be a finite-dimensional vector space, for example. Okay. So if we don't have this term here, this is called a non-interacting theory, and things can be calculated simply, as I'll explain. And Q is sort of the external influence or perturbation you're putting in from the outside sort of sources, and you're trying to calculate the response of the system to Q. So the way we calculate this alternatively is simply to expand this exponential p into polynomials. So we get, this is and it simply reduces to calculating this integral with these polynomials times this Gaussian factor, which is something that can be done in combinatorial fashion. And the result is the famous Fireman diagram expansion. So let's run over these factors here. Well, let's bundle everything up into some combinatorial factor here. We're summing over graphs. And we can draw the typical term in this expansion here in the following way. Let's, for example, have let's have an example here. We have P as the cubic interaction. Like this, with indices on, if you like. And Q, just for example's sake, being quartic, or it could be anything. So to do this calculation here, I draw a vertex for Q, and then vertices for P, n of these. Q here, HP. And then what I have to do is join them together in every possible way. Here's a typical term in the expansion, and this is a graph here. This is my graph gamma, this picture. And this, the expression here stands for a certain calculation involving these tensors here, so Q and P here at the bottom, and each connecting hoop like this is the matrix M inverse. So you can think of this as a calculation in a symmetric monoidal category. And C of gamma is a certain combinatorial factor, some numerical factor that just depends on the graph, the topology of the graph, and not on the Q's and P's. Okay. So, any questions so far? Is that all? Pretty know what I'm talking about.
Or if you get one of these for each monomial, right? So there's many, I mean, P is a shorthand for summation. It's a big, big summation.
Well, P in my example here is just Q, but there could be more terms.
I see.
You'd have to expand that.
Right.
And there'll be lots more terms here.
You say it's a calculation in a symmetric monoidal category, but you're using a lot of extra things there. You're assuming the existence of a background manifold to formulate your integral, and
no, let's assume this is a finite dimensional integral.
okay. But I couldn't present you with a symmetric monoidal category, and there would be a canonical way to do this. I mean, it has to emerge from a.
Oh, okay. So you need a bit more. You need with duals. Sorry.
Probably need a trace.
And this is the standard. This is the standard evaluation. Okay. So with duals, I'll explain in a minute what that means. This thing is a standard piece of the structure.
I think you need a trace on the category too, don't you?
Well, that's part of what it means to say it's with duals.
Okay.
this is all introductory. This isn't supposed to be totally precise.
But the trace is sort of like an integral.
Okay, so what are we doing with braided quantum field theory? Yeah, so these are the Fireman diagrams. So with braided quantum field theory we want to generalise. So we had here a crossing here in our calculation. We want to generalise this to either an over or under crossing in a systematic way. And this was done by Robert Ogle. About 2000. So I'm going to explain a bit how that goes, how to do calculations, and then explain towards the end the appearance of knots and links in this braided quantum field theory. So, so before I get on to the technical part, and to keep describing the physics, right? So, more motivational. So if I'm thinking of three-dimensional general relativity, then you have a particle moving along the world line. This theory. That. This is in a three-manifold. And then you can take a cross-section through that and ask what the geometry should be in three-dimensional general relativity. So I can just take a cross-section there. So that goes through that. Then the geometry of that cross-section in 3D-GR should be a conical geometry. And a cone, a metric cone, has a deficit angle, and that tells you about the mass of the particle. So in 3D-GR, you see it matters whether particles go which way particles pass. So this is not the same thing as that. And so, so a way of thinking about this is that, you see, if I think of one of these particles, say this one here as having a conical geometry around it, then the path of this particle, being a geodesic, will be different whether it passes one side of the vertex of the cone or the other side. You see on this diagram here, you could possibly sort of start over here and go around one side there on the geodesic, or we could go around the back on the other geodesic. Right. Okay, but that's all different. So, Claire.
So something I don't understand is that sort of in the Fireman diagram expansion, those graphs could be construed as featuring simply as a mathematical device of counting certain things. Whereas now they're being upgraded to those curves in the graph actually being thought of as little particles flowing around it. I mean, it makes a difference whether you think of them as genuinely particles, because then braided really is important, or if you just think of it as a mathematical device, because then you wouldn't.
Absolutely, yeah. So that's right. There's a great tension between those two. See, so the classical Fireman diagrams, they're really just graphs. They're not embedded in anything. But normally, when you do this, you think of you're doing physics in Minkowski space or something, and then although these vertices correspond to points in Minkowski space, the actual path sort of isn't anywhere. But you can think of it as the straight line, the geodesic that connects those two. But it doesn't really matter. If you're just in flat space, it doesn't really matter how these things cross, whether those straight lines go above or below. It makes no difference whatsoever to the calculation. So here, if you like, space-time is sort of optional. But once you use, what I'm trying to explain here is that when you introduce braiding, it's a bit like introducing gravity into the picture. Because you see, when you introduce gravity, it should deform the flat geometry in Minkowski space into something with these conical defects in it. And then it does start to matter how these diagrams are braided. And so introducing the braiding is somehow equivalent to putting the things on a three-dimensional manifold. That's sort of if you like, that's a sort of a physics hypothesis, if you like. You can start to think of it that way. But it certainly explains why there's a connection with this 3D quantum gravity.
It wouldn't work for 4-dimensional, it's essential that it's 3-dimensional. Or not? Is it essential that it's 3-dimensional case? Or wouldn't be?
Yeah, so in 4 dimensions you don't have this sort of braiding occurring in this way. But what one hopes for is there'll be some more sophisticated structures. But that's something to dream about. I mean, I don't really understand.
But I guess it already shows up if you're reasoning about anyons or coupled particles.
Yes, in 3D, yes. So in fact, what happened is that Friedel Levine suggested a non-commutative or possibly braided field theory of particles coupled to 3D gravity, 3D quantum gravity, and then a couple of other people showed that this was actually a braided quantum field theory. So this is these guys. This is. So I just said there exists some non-commutative field theory, I gave a construction for it, and these guys said this is a braided field theory. So let's take this idea seriously for a minute and think about what it would entail from a sort of physics point of view. So if you think sort of physically for a minute about a particle propagating from A to B, and now I want to think of it as being in a manifold, so this is really in this three-dimensional manifold. This is a particle propagator, this is a quantum propagator. So I actually want to say it goes along some trajectory there, and then, of course, you see, it could equally well go along some other trajectory, like this, from there to there as well. We go from 2 points. Should I call these points P and Q?
No, wait, is this a three-dimensional space-time still?
So this is three-dimensional space-time.
So we're moving back and forth in time.
Yeah, well, you don't worry about that. That happens.
Okay.
It's all Euclidean anyway, so all the dimensions are on the same footing, so you don't worry about it. Yeah, so when you do quantum gravity, you have diffeomorphism invariance. So, in fact, these two things are the same by diffeomorphism. So you sort of realise that you can't see, the difference between there being a knot on a propagator and there not being on a propagator, if you see what I mean. So locally, there's sort of no way of telling those apart. So if I add in another propagator, propagator here, like this, and the propagator there like that. Of course, the two are no longer equivalent by diffeomorphism, but what's apparent is there's no local way of telling these two apart. So they're locally indistinguishable.
So before you added that red line, you said there was a diffeomorphism.
Yeah. But of course, you see, you can straighten out this to that line at the expense of putting the knot round there on the red line.
Okay.
By you can't get rid of it completely, otherwise you could undo that knot. Okay. So you see that the whole phenomenon is completely non-local.
But you have to use closed curves in your space-time to see this.
Yes, that's right. Yes. Yes. So it seems that when you start thinking about this, and you think about the fact that quantum field theory is still local, the interactions are only local, there isn't some sort of non-local content, you realise that if one knot can occur, any knot can occur. So from the physics ground, if one knot occurs, all do. Question mark, question mark. So when you start thinking from a Fireman diagram perspective, it starts to seem horrendous. You start to think, well, if I start with this diagram here, have I really got to resolve all crossings in all possible ways? And won't I suddenly get, and even worse, haven't I got to put in every possible knot in the intervening propagators here?
No,
And so won't the number of diagrams just explode hugely, and you'll be suddenly counting all possible knots in the diagrams as well as all possible Fireman diagrams.
How are you including the red curve in the problem?
Well, this isn't precise at the moment, so I'm going to make
I mean, because without the red curve,
through us.
you can't actually, since we're not worried about time, you can't actually untie the knot. You can just loop it around the end point.
That's right. Can't untie them. So too many Fireman diagrams. That's the sort of the big worry. This might lead to too many Fireman diagrams. Now, I'm about to explain the formalism of braided quantum field theory, and as I'll explain in a minute, when I first looked at this, and I talked to Robert Urkel about this, initially we couldn't find any knots and links in the Fireman diagrams at all. So the other conjecture from the braided quantum field theory that then developed at that time is there weren't any knots or links in these braided quantum field theory diagrams. So this is an alternative conjecture.
Can you use some intuition on this?
Yeah, I'll draw some examples in a minute.
Okay.
Well, you know knots and links.
Embedded graphs don't knot. You can unknot them.
No, that's not true. So that was weird as well, and it was pulling in completely opposite direction to this thought here. And it turns out that these both get resolved, and it's actually both worries get resolved at once. There are knots and links. So there are knots and links. But you only get finitely many at any order in perturbation theory. Only. Finitely. Only. At any order. In perturbation theory. So that's what I'm going to explain. So order means the number of p's. Okay. So, now I need to explain something about braided quantum field theory. So I'm now starting to talk, as it were. So we start with a braided monoidal category of duals. So braiding means there's a particular morphism like this, for any pair of objects, and its inverse is drawn like this. And duals means that for all objects, there's an evaluation. I've said this the wrong way around. Different order. So firstly, there's a contravariant functor. Takes something to its dual. And this is involuntary. Preserves the grading in the right kind of way. And then there's evaluation and co-evaluation. This is for y. This goes from y. Tensor y. K, which is the ground field or the unit object in the knowledge category. And y star. And the co-evaluation of y goes from and among the relation, we draw these like this. This goes from, so I'm going down the page, and usually it goes from y to y star. So the unit object is nothing, and this one here is drawn the other way. And you have the usual relations among these things, and the obvious Reiner-Meister type moves. And for example, this is related to the duality functor the following way. So this will be, this is y and this is y star. For all y and for all f. Okay. And I want to assume for concreteness that this is a category of vector spaces. So you don't have to assume this. You can make it more abstract. Objects of vector spaces. I want to talk about elements of the objects, element of the vector space. You can reformulate it so you know.
You've done F as an endomorphism, the same domain and codomain. Is that
I'm sorry?
You've done F as an endomorphism with the same domain and codomain. Is that right?
Yeah, no, it's not. No, actually. Yeah, you're right. It could be anything else. It could be Z.
So when you say objects of vector spaces, do you mean it's like a fibre functor or it's a subcategory of vector spaces? Or?
Yeah, so if you like, there's a model everything functor to vector space. So think of examples like the representation category of a quantum group. The
Wait,
objects
but
are
then the tensor product is a truncation in it, so it would be.
yeah, but that's on the morphism, it's not on the vector space.
Right, okay.
Okay, so so we pick X, and that's going to be your space of fields. And X star is of course the linear functions. And then by X star hat, I mean the X star meringue and the just, if you like, the polynomial functions.
So is that like a symmetric tensor product, or?
No, ordinary tensor product.
Should that be an X star on the right side?
I'm sorry?
Should that be an X star on the right hand side?
Star. Thank you. And in fact, this thing is a braided hot foundry graph. Turns out. I'm not going to go into all the details. But the way you should think of this is that X is the space of differentials on So this is some vector space, this is all polynomials in the coordinates on that vector space, and the differentials are the partial derivatives in the various different coordinate directions.
So I'm just, is that, we've got that direct sum, like how do you take this infinite direct sum?
Well, yeah, that's a good question actually. Just finite, formal things with finite many entries. But in a minute I want to use a gadget which has infinitely many entries, so
you'd only get a hop algebra if it actually had infinitely many, wouldn't you?
Yeah, okay. Not worry about it too much. Okay, so no, I think no.
Oh, sorry.
No, that's not true.
Sorry, okay.
That's fine. It's fine.
Yeah.
So if delta is an element of x, this is a partial derivative, and alpha and beta are polynomials, then the upshot of all this, there's some abstract sort of stuff here, stuff that Charles Margie invented, I guess, tells you that there's a you can think of this as a differentiation obeying the braided Leibniz rule. So there's a mapping, so delta. This. So delta is a mapping from, defines a mapping from, in fact, there's a differentiation operation which goes from x tensor x and this informal notation here means you differentiate. That's what I mean by here. And the differentiation reduces the degree by 1, as you expect. Okay, so this is like the usual Leibniz rule here, except that you have to put in the braiding in the right way. And it says, roughly speaking, to differentiate a product of two things, you need to move the differentiation operator past the alpha to differentiate the beta thing. So you need to flip these two things over before you're allowed into attack. So this operation here means in this tensor product here, this will be in the tensor product of x, this flip thing here, then this second factor here differentiates the beta, leaving that then to multiply the result. That's implicit notation there. That's this line here is it, and then differentiate here. So explicitly, you can solve this explicitly. I'll do that in the next. And sort of make more sense possibly. There's then an expansion, which you can do by using this thing inductively here. Is n. N is a braided integer. And it's a sum of terms, and there's n of them. So it says so if this alpha is of degree n, so this is an alpha n x star n. So if you think this as a sum of monomials of degree n, when you differentiate, there's n terms to differentiate, and for each one of them, you have to pull the term you're going to differentiate back to, that's this string here, back to the first lot before you then differentiate with a d. So this is all a dual picture to this picture here. That's why psi appears rather than psi inverse. This would be like as a solution of this abstract braided Leibniz rule. There's X star on each of these strings. Pretty happy with that? And what we want to define to do our field theory is the expectation value of polynomial, which I called earlier Q, but I'm now calling alpha. I guess I could carry on calling it Q. Now I want to divide by normalization factor W. The W is a certain Gaussian weight. And this is where I really need some completion, because Gaussian may have an infinite number of terms. But we don't seem to actually have to worry too much about the fine detail of this. It would be nice if someone did. This is a Gaussian. So Gaussian should be defined by a quadratic form. That's a quadratic form. Alright, yes. So we're going to pick W and gamma once and for all. And the equation is that W is, if I differentiate W, so that's the usual property of a Gaussian, that if you have a Gaussian determined by a quadratic form, and you differentiate it, all you do is you multiply the Gaussian by some linear factor, which is linear in that differential, depending on the quadratic form, in the exponent of the Gaussian. Commutatively, you would be thinking of W as into the then finally your integration, you need to define. Obviously it's going to be linear functional. And the only other thing you need to know about it is you have an integration by parts formula. Okay, and then that's enough to define this by concrete calculation. So I'm just going to produce the formula for this. So what is this? This is a function from x star n to the ground field for each n. And by dualization, by applying the star, we can just regard that as I'm going to do that. K to x to d. Okay, so this is a function. Let's call this z star. This is zn. So we have the braided width theorem. It's stated by well, I think not even Kemp had a role in it as well. So z squared, or z2, second order part of z, is the following calculation. Braiding composed with gamma inverse density composed with covariation. So that, in other words, you can draw a diagram. So the composition means I start here, so do curve valuation, and x is that way. Should be x. Do gamma inverse in there, and then finally I do the. So that maps me top to bottom from the ground field to x tensor x. And that's the propagator in the theory. So I'm going to draw this way. And there's no arrow on this, that's how this is distinct from that diagram. Okay, and then the higher order things explained. Z2n, no odd ones, is a braided double factorial times the propagator to the nth. I'll explain that by just doing some examples. N equals 1. Well, this braided factorial is just 1, so we just get the calculation had before for Z2. Yeah. Z2, I'm calculating Z4. This. And 3 terms. And you see you have the number of terms you get is equal to the number of this classical number here. So the braided, the normal double factorial is 2 to the 2n factorial over n factorial times 3n. In other words, it's 1 times 3 plus 5, 7. So how much time do I have?
About 10 minutes.
10 minutes, okay. And then if you want to do n equals 3, what you have to do is take the n equals 2 result, this is sort of an induction thing, stick another propagator on the beginning, oops, yeah that's right, and then I compose underneath with, in fact, the braided 5 double factorial. So I compose with and then you get 15 terms. You compose each of these terms of each of those, and so on. And you can describe this as follows. So I hope you're getting the idea that there's a coherent body of theory here, and that when you pick that braided Gaussian integration and so on, everything gets determined. So we describe this as follows. For every partition of 2n into pairs, you draw the rightmost hoop first. Example, if I want to get the term when I want to describe this term composed with that term there, I can draw that in the following way. I have 6 objects down the bottom here. The rightmost hoop is that one, I draw that one first. So rightmost means that the left-hand leg is the furthest to the right. No, that's wrong actually, it's not the rightmost hoop. The rightmost hoop is this one here, so I draw that one first. Then you put the others underneath. So the next rightmost one is this one here, because it starts that one, and then finally I draw that one there. Okay? And you can see that that's that composed of that. And I now have myself here a right mouse to move of sliding that over that there, so it doesn't intersect. Okay, now if we want to do the interaction theory, we compose with did the Gaussian integration in interacting theory. Treated it not contained, treated it K. Used it anywhere. And there's a number of these things here, K will be smaller. So for example, if I want to do so P is cubic, I would do, this would be a term here involving P to the 1, and this here would be, well, this would be a term involving P squared, that's P as well, this is P squared term and Q is 1. That would be a vacuum diagram. And you can see here that this is in fact unknotted. You can, by right arm moves, you can just slide this around here. So there's no knotting or linking going on. So the question when I first met this, and when Friedel and Levine suggested that there's a braided quantum field theory involved in 3D gravity, my first question was, well, I was having these sort of physics worries here. But firstly, does this have any knots and links in it, this theory? And secondly, if it does, surely that would sort of be too many in a sense. So I'd end up with something that couldn't use the usual Feynman theory. Because I'd somehow have to sum over all knots on any given propagator. So I was sort of worried about it both ways. And it turns out this theory does contain knots and links. So this is cutting one step short. So firstly, Robert and I did some calculations. I remember I met him in, I think, 2005 at a conference. And I spent the whole journey home waiting at the airport and so on the plane, drawing diagrams, trying to find a knot or a link diagram. And I couldn't find any at all. And when I got home, I emailed him and said, look, I couldn't actually find any knots in your theory. Maybe it's sort of trivial. And he said, no, I don't think there are any. I couldn't find any either. So that sort of became the conjecture that was wrong to me. But it does, actually. So theory contains lots and links. And we'll see why we couldn't find them. So I realised this in last November at the Schrödinger Institute, because I was trying to explain to them why this Friedel-Levine theory was trivial, because it didn't have any knots and links in it. So in the process of trying to explain it, I found out where they are. And the point is you have to go through very high order diagrams. So for example, this occurs, this is in a cubic theory. This occurs first, and the minimum order is 6 for a link to occur, and then you get the hot link. And to actually get a knotted diagram, you actually need to go to 7th order. So if you draw this diagram here, there is actually, with K of 7th order diagram, that's the minimum you need, you can get knots. So this is the hot thing. In fact, the one I found was the trefoil. And so this diagram here, this thing here, which I haven't drawn, is knotted. And now you can see why it's not easy to find these. You see, if you follow the description I had there, then what's the value of this n here, these calculations? Well, n here, you see you need 6 vertices, so n is 3 times 16, the vertices, and then the external legs is 1, 2, 3, 4, 5, 6 external legs as well. So you have 24. And 24 double factorial is huge. Well, actually, I've worked out 21 double factorial here, and that's 13 billion, so 24. So, you see, just by playing around with a few low-order diagrams, even the length of time it takes to wait in the airport, you're not going to get anywhere. So, in the end, I managed to find some examples. And here they are. So, let's have a colour from my examples. So, what I'm going to draw is, assuming I'm in the cubic theory, and I'm going to ignore on each vertex, there's one external leg which I'm going to ignore. So I need 6 of these. 4, 5, 6. And then I'll start with the rightmost thing and go over. So I'm going to ignore that. This one goes there. There. And this one. No, this one here is more rightmost. I want one to go here around here. So I'll go that first, and this one can go there. And then this one here. No. First, this one here. And these are all external legs, so they'll. I mean, you don't need to put these in. It's just so they all come out here. There's the 6 external legs in this diagram here. And then if you stare really hard at this, you can see that there's a hot link. If I've drawn it correctly. Does anybody see a hot link?
Wait, there's supposed to be 3 loops?
There's 2 loops.
2 loops. Wait, the hot link, you mean just they're linked simply once?
Yeah.
We should just
Yes.
count the number of crossings.
Yeah,
Yeah.
Okay, thank you.
One's over, one's under, and then that pulls back, so then we do it,
Yeah. But if you do this with any fewer vertices, you start with 5 and draw anything, you get nothing at all. So I think at the airport, I remember I exactly stopped at 5 at the airport. Okay, and how do I get a knot? Well, now I've got to have 7 of these things. And I'm going to miss off the external legs here and put them in.
Now, exactly why are the rules that you can't go back and forth? You can only go around and then over or under. Why is that the rules?
Oh, you mean why is this the braided?
Yeah.
Oh, you just have to do some algebra. I mean, that I've done to explain that. But it's implicit in that differential calculus, which I wrote down in the first place. So let me do this example here. So let's do the same thing with the trefoil to get the trefoil. So I'm going to again hop 2. I've probably made a mistake already. If I want to hop 2, and I don't want to do that one yet. This one's got a hop to the end one there. Then that one hops to there. And finally this one hops underneath. Whoops. To there. Okay, so this is the hop thing. This is the trefoil. Now I assure you there are lots of ways of getting the unknot. Lots and lots of ways. I haven't attempted to count them, but here is a trefoil. There's a few other ways of getting a trefoil I know about. I haven't found any other knots yet. I suspect that at all the 7 you only get the trefoil and nothing else. So I conjecture that you get all knots and lengths this way. But this is a pretty shaky conjecture yet, because I've only found 2. I guess to really seal it, I need to find the figure of 8 knot and then do the body. But I think you probably need to go to order 8 to find that. I guess. Because I can pretty see that's the trefoil. Shall I do some? I'll do a bit of surgery on it and then you can see it. What we do is I'm going to randomise to move that thing over there so that it just closes like that.
It looks rather like a flat representation, you know?
It does a bit, yes.
I mean, you know, you can get any knot with a flat representation.
And I'm going to pull that up like that there. So it's going to close across here. And then you can see that's a trefoil. That it's got 3 crossings, 1, 2, 3, and they alternate over, under, over, under, over. Yeah, that's right. There ought to be things to know about. So I guess I ran out of time.
Are there any questions, comments? Yes, please.
Yeah. Did you ever ask the question if you can compute the result if you have one cells? Does there exist a 2 cell to go in from them? Does there exist such a diagram to go from one to the other?
2 cell.
A diagram like this.
So if I do what?
Okay, with your entries, your x's or y's,
Yes.
for me the 1 cells.
Yes, I see.
Your diagrams are the 2 cells,
Okay,
the
fine,
morphism in that category. So you
Yes.
have a non-symmetric.
Oh, is there any? Can you realise any?
It's compact, but it's not free because you have this special axiom that's self-dual.
Yes.
So if it's compact and free, you can really compute all the existing diagrams. So what you do, you have much more, because you collapse objects, 1 cells.
Yes.
So the question of computation, has it any interest for you?
I see.
If it's computable or not, the existence of these things, or decision procedure.
So you mean if I have any? If I have any? See, I'm only really having objects on the bottom. I don't really have anything on the top. So.
Well, that comes to the same because you can always.
Oh, I see. So
you can always make them all the same.
So if I have any number of x's on the bottom, can I run them all?
Right.
Or yes, if it's even, no, if it's odd.
You can just link them all. What you did just derivations there in a special kind of logic.
I see.
So it's much stronger than free compact linear logic. Compact linear logic much stronger what you have there.
Yeah. Well, right. Yes. No, this isn't. Yeah. I mean, so the results about braided monodal categories. The braided monodal category is the free monodal on something. It's whatever relations, but no, I don't know anything about that for this case. It's a very particular integration theory.
I think I sort of missed it. How did you define your interaction? But you seem to have a sort of 3-point interaction vertex going on there. I think I missed how that.
Okay, so I guess
entered into.
Yeah, I skipped that part. So I guess what I'm doing is doing the integral of e to the p.
But when you say integral, this is your sort of internal categorical.
This is your braided integral, with the Gaussian weight w. And then you expand this as an ordinary exponential here.
So how do you? What is p exactly? That's your get.
So p is my. Well, in this example, it's this cubic function. So t is in x hat star. So I'm just doing this expansion here.
Okay. So you can pick that freely, can you? You can pick any element of the polynomial algebra.
Yeah.
Okay.
Now,
And of course, this. Sorry, just a minute. And of course, this again. This isn't in this finite direct sum and so on. There's some completion involved here, but I think that kind of. If you just expand up some order there, then this doesn't live in the right thing. So, I think the whole calculation is sufficiently computational that you don't have to worry about.
Yeah. And sorry, Louis, you were asking.
Lewis.
Yes. Does this integral have some function in the category? I mean, you just define the integral somehow, or where does it come from? What is it?
What is it? What is it? I mean, it's a possible extension of Gaussian integration into this braided setting. Whether it's some special gadget in the category, I don't know. I mean, maybe there is some intrinsic categorical explanation of it.
Oh, so it's just, at this point, it's just some formula.
It's just a formula, yeah.
And the formula works on things that are polynomial times Gaussian.
Yeah.
So it's sort of built up piece by piece.
Right.
And what you have is you're using something I want to say is like Q combinatorics here. To generalize the formulas from calculus.
Yes.
And that's what you get. Okay.
It's actually very reminiscent of the Kaufman's explanation of the Jones-Bensel idempotence, where you resolve symmetrizers into these braidings with all the same braid used, not the inverse braiding. So, I mean, that might be interesting.
So you can get actual numbers and things, right?
Oh, sure.
So what happens when you do those braided categories from quantum groups and things? What kind of numbers do you get out?
There's a bit about that in Robert Oaker's paper. He says you can apply it to 5-4 theory on a two-sphere or something and have a braided two-sphere. He claims it's better than the usual thing, so but it's all in his paper. I don't claim to have any insights into it.
How does it interface with the usual TQFT variance?
Manifolds?
Yeah, the ones, the kind of things that you do in TQFT when you calculate from braided monoidal categories.
Oh yeah, right. So what you do is so the 3D gravity thing is so you if you have a manifold, if you have a free manifold, then you then when you have a braided model category, this gives an invariant here for free manifold. So partition function. And you can extend this to invariants with an embedded graph in the manifold. So you can have an embedded graph or something. And then you get the invariant for the manifold and the embedded graph. And if you take, let's take the case where you have a free sphere here. Then the idea is that this partition function is identical to this evaluation of the Fireman diagram here. So an alternative way of calculating these, each individual Fireman diagram, I mean you can either do it by just doing the categorical calculus with R matrices and so on. Another way of doing it is to embed it all in the 3-sphere and calculate the TQFT invariant with this graph here.
Would that be the Aarhus integral?
Sorry?
Would that be the Aarhus integral that you'd use for this?
I don't recognise that.
Right, this the sort of universal perturbative invariant of Barnett and Gauss-Leaders presenting in terms of.
Well, actually no, because that's probably. No, I don't think so. Actually, I think that's the expansion of the trivial part. I just take ZS3 and expand what that, you get all those sorts of perturbation theorems.
Right.
But maybe. Well, maybe the answer is yes, but you have to take this thing and then expand this in the Q parameter. And then maybe you get that perturbation that we're talking about.
I suggest we leave it here and we take a 15 minutes break because otherwise we're reading too much those papers. So we thank the speaker.